Okay, we can start now. Yeah, so this is your week 2, and you have already seen week 2 lectures. I mean, the videos and the lectures are already uploaded on your NPTEL portal. So yeah, if you haven't seen them yet, please go through them as soon as possible. And also, I think week 3 is also out, and it is on the way and soon. So more lectures are on your way. So just try to be I mean, uh, try to cover those lectures as soon as possible, because I mean, if you keep them at the last, it would be a huge load for you at the end, which possibly not good enough to handle at the end. So this week, in your week 2, you have seen topics related to coherent states. So that is what we will be also discussing right here, and also if any other questions related to the course or any other problems that you didn't understand well, or also anything in the lecture, you can always ask here. So yeah, we are here to interact and discuss and resolve issues regarding the topics that has been discussed in your course. So now we will discuss coherent states. So Okay, I will just give you a brief idea about what are coherent states. But it is already I mean, explained well by the instructor in the lecture videos. If you would see, those are in more detail. I will try to give you a brief overlook of that topic, and then we'll try to solve some problems on it. So yeah, so. Uh, yeah, coherent states. So you can able to see my screen, right?
Yes, sir.
Okay, thanks. So coherent states, like how, what does this do? I mean, so basically, in quantum mechanics, you will see some coherent states denoted as alpha, or could be some other notation as well. No issues with that. So these are states. These are states uh, having indefinite number of quanta, meaning they are basically uh, linear combinations of n states. So let me write this in bracket. These are eigenstates. Basically, alpha is some linear combination of eigenstates. Just like how there are eigenstates and some other states which you often encounter in quantum mechanics are linear combinations of those eigenstates. So those are superposed states. So among them, alpha is also one such superposed state where you will see uh, that uh, like this alpha uh, is some linear combination, and this n can be infinite. It has no bound. Like there are infinite number of eigenstates. So this n are eigenstates. Could be of any given system. But more preferably we'll look into harmonic oscillator system, particularly where this coherent states, the topic has been quite well established, and it is easy to understand, like when you start understanding this topic. So yeah, so this is again, yeah, this is a linear combination of eigenstates where you will find uh, for where you see that this alpha, where let me write such that where alpha uh, are eigenstates of lowering operator A. So yeah, where so I think you are familiar with raising and lowering operator, which is like discussed very well in the context of harmonic oscillator system. So you can think of that here. So the lowering operator, which the purpose of lowering operator you might have seen, if you add that lowering operator on a eigenstate of nth eigenstate of a harmonic oscillator, you get some state something like some constant, let's say some yeah, some constant, let's say bn times bn n minus 1. So basically if you add a on n, then you get n minus 1. Likewise you have a dagger operator. So this is a dagger operator. If you act on uh, n, then you basically get n plus 1. So these are basically lowering and raising operators. So among them, this lowering operator, you see when if it is acting on the energy eigenstate, so it is not a eigenstate, this n is not eigenstate of a. So this n is not an eigenstate of A. But here, if you act A on alpha, you get this alpha alpha, where you find this alpha is the eigenstate of A. This alpha is eigenstate of A, and with eigenvalue is alpha. So this is the eigenvalue. So this is something special about coherent states. So one such example, for example, if you consider one of the example of coherent state, that would be uh, zero. Zero of harmonic oscillator system, where you if you act A, so this is the example. So if you act A, you get 0 0. So basically, I mean, from this rule, you would say if A acts on 0, so it is basically 0. So otherwise, I can write this way. So yeah, so that is the like understanding of I mean the first or the basically the definition to definition about the coherent states. And yeah, and remember this alpha is your eigenvalue. This alpha is your eigenvalue, and it is complex. So so basically you can write alpha as because you can write any complex number in this way. Uh, uh, Something, I mean, it has a real part and a imaginary part, or in a exponential form, you can write it as this. I mean, the phase part and the real part. or the magnitude value. Magnitude contains both real and, I mean, it is basically the square root of I mean, if your complex number is x plus iy, then your if I call this as alpha, then mod alpha will be x square plus y square. So yeah, so that is I hope you know the one of the way to write complex numbers. So this is just like alpha is like one of those complex numbers, right? So okay, then yeah, and before moving on, there is one more thing about uh, this topic, where you have something called displacement operators. So what are displacement operators? So where displacement operators is denoted as these are operators. So d hat alpha is exponential alpha a dagger minus alpha star a, or otherwise you can also write this as what are these displacement operators? Basically, these are the displacement operators which you require to construct coherent states. So, using this d alpha, you can construct basically alpha coherent states for different type of quantum systems, and this d alpha is important, without which you cannot achieve any kind of coherent states. So. Um, and core states, here we are just discussing like about some definitions and what it does and some properties, but it has a important meaning to many other things. So for example, I mean, this displacement, for example, this core states, they are very important in quantum optics. So I mean, in quantum optics, this coherent states, like it has quantum optics uh, importance. I mean, uh, these states are given more important in quantum optics, if you would see, because they explain the classical light. These coherent states can basically explain you classical type of states. So why classical type? Because you would see that in coherent states, you will find the states to be in definite. You will describe your quantum state or operator in a defined, in a proper definite state. For example, what I mean, last week, which we saw, if you take expectation value of a position operator in a quantum harmonic oscillator, in some of or in any nth eigenstate of harmonic oscillator, like you get something related to, some h bar 2m omega and some other factor multiplied to it. Let's say uh, some c1 or something. You take any other state alpha x to be something, let's say some psi. So where this psi is some linear combination, let's say, where psi is some uh, 1 by root 2, uh, 0 plus 1, some state. But if you take this expectation in coherent state, that is alpha, uh, uh, you will find this would come out to be something like something similar to x naught uh, sine something x naught sine omega t and some phase, let's say phi. And this is something, classically also we write this. Uh, uh, how do you write classically the displacement of a harmonic oscillator system? Like you have seen such harmonic oscillator system, whether it's simple pendulum or or some other pendulum system, like you write this displacement operator or displacement vector is something of this form, x naught sine omega t with some phase. So and if you take the uncertainty in x, or the uncertainty if you would calculate associated with x, you'll find the minimum uncertainty because it is definite state, that alpha denotes a definite classical state. So I can write here alpha denotes definite classical state. So yeah, so that is something to motivate the need of uh, uh, coherent states in the context of quantum optics, or any other places where if you find these coherent states are quite important. So yeah, so yeah, this displacement operators, uh, they are required to construct coherent states. and and this and this displacement operator also you can write or d alpha, d alpha you can also write exponential exponential minus half alpha square modulus alpha square, then alpha a dagger alpha star. So this is just the other way of writing this d alpha. So this same is this thing which is written here. So like how this can be written, like there is a rule called BCS rule, Baker Hausdorff, Baker Campbell Hausdorff. So BCH rule. So in BCS rule, like any operators. So maybe I can explain this a bit here. So using BCH rule. Yeah. So, what does BCS rule do? I mean, like for example, we wrote this operator d alpha, this displacement operator. We or otherwise we re-express this d alpha, something of this form, where you see where you had only one exponential, and you find its exponent or the power right here, which was alpha a dagger minus alpha star a, but now that is splitted into three exponentials. So that is done through this BCS property or BCS rule. So this rule says that if you have exponential a, then b exponential minus a. So you can write this where a, remember where when I say this d alpha is operator, uh, this is basically operator due to, because you see this a dagger and a operator, they are written in an exponential form. So this alpha is some value, some number, but this a dagger and a are operators. So here also, if I say a b are your operators are, and so this is important because you see this property says that you can write this as b plus ab plus uh, 1 by 2 factorial, a I mean b plus commutator of ab plus 1 by 2 factorial commutator of a with commutator of ab, and so on it will go on. So uh, so and if you write exponential of a, ea and eb, then it is eb, ea, then exponential of commutator of ab. And so I will let you know soon why these are important. So these are some rules which you can use them uh, in your when you are working with displacement operators or coherent states. So why I'm doing so? Suppose like if like if you have some exponential of a and exponential of b, and where a and b are some numbers, you can just simply do this e to the power a plus b or something, e to the power a, then e to the power minus a, then this is basically 1, because e to the power a minus a, I mean e to the power, this is basically a minus a, so this is e to the power 0. But these things will not uh, work. I mean these are incorrect if a and b are your are operators. So you cannot do this. So because operators, they I mean when you take exponential of operators, then they have to satisfy this kind of relations. So you can see from BCS root, if you take e to the power a and e to the power b, then then you cannot write e to the power a plus b. Rather, it is e to the power b, e to the power a, then e to the power commutator of a. So, but in case if suppose if you have uh, like for example, if you have some uh, e to the power a, e to the power b, you can write this as uh, what I'm saying. Yeah, e to the power a and e to the power b. You can write this as a plus b if a b, if commutator of a b is 0. Like only in that case you can have this, like for example, which you can see from here. So if commutator of a b are 0, then yeah, then that is basically e to the power of a, e to the power of operator a multiplied with e to the power of operator b will give you e to the power of operator a plus operator b. So yeah, so that is some information to remember when you are working with displacement operators, because you will be repeatedly having this kind of exponential operators where uh, in the power of your exponential you basically have quantum operators, which like these are basically matrices. If you represent if you write down its representation form, I mean if you write down uh, in a mathematical form. So these are in abstract mathematical notations. These are basically matrices. So A, B, all are matrices. So uh, so when you do e to the power of A multiplied e to the power B, then that is equal to e to the power A plus B if they are numbers. But if they are matrices, you cannot do that. So this is you have to follow this rule. Uh, so, uh, if it is e to the power of matrix A multiplied with e to the power matrix B, then again it is written something as e to the power matrix B and e to the power matrix A multiplied with e to the power of commutator of matrix A and B. So that is how. So yeah, now so if you have any kind of issues, or if you didn't understand anything about or any problem, or you can tell. uh, Is everything fine, or any questions? Anything? Uh, you can speak, like if you can unmute and speak. Any questions, or is it clear?
No, sir. Yes, sir. Clear, sir.
Okay, okay, fine. So yeah, so we can see some questions right here. Uh, so using this displacement operator, uh, so the first, we have to prove some of the properties of displacement operator. So you see, in the first case we have to show the I mean, yeah, in the first case we have to show, if you take the uh, transpose of or basically, I mean the uh, transpose conjugate of displacement operator and multiply with displacement operator, or basically when you do a dagger a, so with the operator, and if you get identity, then that means it is a I mean, I'm saying, if a dagger a is your identity operator, then uh, a is your unitary matrix. Unitary matrix, or your unitary operator. To prove this is a unitary operator, this displacement operator, we can uh, start, like I mean, we can start proving it in the following way. So d alpha alpha a double minus alpha star a. So this is how it is, we defined at the start, the displacement operator. So you start with the definition, and then uh, let's calculate what is d alpha of transpose, or basically dagger. So that is uh, e alpha a dagger minus alpha star a dagger. Then here you can write alpha a dagger minus alpha star a dagger. Then uh, here you see this uh, A and A dagger are your are lowering and raising operators, uh, of, let's say that harmonic oscillator of harmonic oscillators. And if that is so, this, I mean, if you take this, yeah, they have a relation, commutation relation, that is equals to identity. So, these are a dagger that we are dealing here. They are basically raising lowering operators. So if you see that when I in this part, if I take alpha dagger, so alpha is a number. So but dagger means we have to do transpose and uh, conjugate. So for a number, transpose is nothing. There is, no meaning about transpose, but you can take the conjugate. So because dagger means transpose and conjugate at the same time. So if you take uh, conjugate of alpha, that is alpha star, and then a dagger of dagger is a, then you have, similarly you will have alpha and A dagger. And yeah, now you can see here I can write this as minus of alpha A dagger minus sorry, alpha star and A. So this is basically D of minus alpha. And uh, and to and ho- yeah, so this is D of minus alpha, because you see uh, D of alpha is this. If D of alpha is this, then you can write this as D of minus alpha. Then from here we also know, if suppose if D dagger alpha and or for any if A dagger A is identity, then you can write A dagger is A of inverse. So using that, we can also say uh, I can also write D of alpha dagger is also D of minus alpha, or yeah, D of I can write as D of alpha, yeah, uh, D of alpha minus 1, or otherwise, you see, from here we found D of alpha dagger equal to D of minus alpha. Right? From here we found this is, and also we know D of alpha is also can also be written this way, because for that is true for any matrix or any operator, that is A dagger A equal to identity operator, then A dagger must be also equal to A of A inverse. So so with that we can say that this implies D of alpha inverse is equal to D of minus alpha. So so from here it says that your D of alpha is a unitary operator, because uh, I mean you showed your your D of alpha, D alpha dagger is equal to D to the D of minus alpha, and also D alpha inverse is D of minus alpha. So that means your uh, D of alpha dagger is equal to D of alpha inverse. So that says that your D alpha is a unitary operator. So, okay. So could you get that, or any problem? So so basically, if you or you can directly check here. Let's say you got D of alpha dagger and D of alpha. So you calculated what D of alpha, which you found out to be this D of alpha dagger, and D of alpha, which you know the definition. If you do write both of them, so let's that is alpha A dagger minus alpha star A, and alpha A dagger minus alpha star A. So you see, these are um, this you can write as 0. Uh, uh, Here you see this is your D of minus alpha, and this is your D of sorry, this is not 0. This is your identity operator. This is your D alpha. So uh, Here this is basically e to the power minus a, and e to the power a is identity operator. So again, as I said, you can write in this case e to the power minus a multiplied with e to the power a equal to identity operator. Otherwise, I mean, you can write this in this case particularly because you see when a commutes. I mean, if you take the commutation of a, that is basically zero. So commuting with itself is always zero. So in that case, it is only, I mean, it is still valid if you just simply write minus a plus a, that is just I. But if it would have been some other matrix, let's say this would have been some b, and if a and b doesn't commute, then you cannot have written this as minus a plus b. I mean, this would have been wrong. So yeah. Fine. So this is like how you prove this is your identity operator. So any issue or any problem, uh, you can speak if any problem is there. So did you all understood or
Yes, sir.
okay? So the next you have to prove d of alpha dagger is a. So yeah, this d of alpha I'm sometimes writing as uh, I'm writing d alpha dagger or sometimes or d dagger alpha. So I basically mean both are same. So don't get confused with that. So right now, what will be this? So this is something you have to prove this one, a plus alpha. So yeah, we know against uh, we can write what we found the alpha dagger. So we found the alpha dagger as uh, let's write this as e alpha star a minus alpha a dagger, then a e to the power alpha uh, alpha a dagger minus alpha star a. So you see, this is something of this form: e to the power uh, a times b e to the power minus a. So again, you can this is coming out to be again some kind of uh, exponential power of operators or matrices, and again, whenever you have this kind of situation, remember to think about BCS root. uh, you just cannot simply multiply how you used to do with if you are dealing with numbers, which is not the case for when you have operators. So yeah, so you can follow the BCS rule as I presented you before right here. So you can see the situation that we have right now is something similar to this property, which you can follow this. You can write this expression. You can write this to expand your uh, expression, which we started right now. So this is from here we can write. Maybe I can. in this part. So using yeah, using BCH rule, we can write our expression as uh, so. So if you first comes B, so if you are calling, let's say you call this as A, this is your B, and this is your minus of A. So so uh, B in our case is operator A. So B is our operator A. So first we will have operator A, then plus commutator of AB. So A is this thing. So A is this thing. So plus commutator of alpha star A minus alpha A dagger. Then commutator of A and B. B is A again. That is, yeah. Then plus half factorial. You again have alpha star A minus alpha A dagger. Then alpha star A minus alpha A dagger A. So this is a nested commutator. You have commutator within commutator. So yeah, you'll have more such nested commutators as you go on in the series. But you'll see that we are using up to these terms because you'll find that once one of these term goes zero, the other terms will also subsequently go zero. This doesn't happen, almost every time, but in some cases, like here particularly, it does. So in most of the cases, you will find this thing happening. Uh, yeah, for example, let's write the first term we have A, and the second term you have to calculate the commutator. So you have to calculate this commutator. So if you calculate this commutator, let's uh, see how you can do that. So first, this commutator you can write it as uh, yeah, you can write it as alpha star A, or basically you can write it as alpha star A A commutator minus alpha A dagger A commutator. So commutator with commutator itself is zero, and A dagger A commutator is minus one, as I was telling you before. So in quantum harmonic oscillator, uh, we know this. A of I mean commutator of A and A dagger is 1, so that means here it will be minus 1, so you have plus alpha. So from here you get plus alpha, then you have plus 1 over 2 factorial, and here you see the first uh, term right here. You have alpha star A minus alpha A dagger. Then this commutator is same as what we saw right here. So this is same. So I can write it as A, which we found out just right now. And then similarly you have more terms here. And now you have to uh, calculate this part. So what does this will give you? Uh, so this is, yeah, I was wrong here. This is alpha because yeah, this gives you alpha. The first term is 0, and the second term, this gives you minus alpha, right? No, this gives you plus alpha because a commutator is minus 1, and minus 1 times minus alpha is alpha, right? So uh, here you can write uh, a plus alpha plus, and again this commutator which you can calculate, alpha star a and alpha, uh, or basically this is alpha star and alpha, basically a commutator with identity operator minus uh, uh, wait a minute, there is, we got alpha from here, uh, yeah, it's fine. So basically this alpha, I mean there's no point of writing this way because you know already this alpha is some complex number as I said before. So this is just some operator because you have a and a dagger, and alpha is some number, and if you do commutator with operator and some number, so basically this is zero, so this is telling us something a and alpha commutator where alpha is some number. I can write it as alpha a times identity operator, so that is zero. So yeah, I was expanding this and writing so normal because it is trivial that it is zero, so plus 0. And same way you found if this term going to be 0, and same way you will see that other higher terms will also go 0 likewise, which I have not shown. So that is why in the series itself I have kept up to 3 terms, because most of the time this is enough to uh, I mean write down your expressions when you have this kind of exponential operators. So yeah, so here you finally proved your relation that uh, d of d dagger alpha and a and d alpha is a plus alpha. Right. So likewise, you will have other term that will be also zero. And yeah, same way you can try the other case, the third case, which like which will give you the similar way. I mean, or maybe I can show you quickly right here. So the third case we have d dagger alpha a dagger d alpha. So I can write this as e of alpha star a minus alpha a dagger to the power alpha a dagger minus alpha star a. Then using again BCH as we did. So if you call this is your B, then a dagger will come here. Then commutator of uh, alpha star a minus alpha a dagger plus 1 by 2 factorial, and you have the commutator right here. Again here also it will go to 0 if you evaluate, and from here you will get uh, a dagger plus from alpha star. So commutator of this thing will give alpha star. So yeah. So so did you get or any issues in this problem? Uh, Anything that was not clear? Any problem you can speak. Yeah, is it clear, or if not, I can explain.
Fine, sir. I'm clear with it.
Okay, fine. So then next we can discuss this problem right here. So yeah, as I said, like before at the beginning, the displacement operators that we discussed some of its properties, right? Just now in the first question. So where this displacement operator is basically now you can use to construct coherent states, the coherent states that we started our discussing with. So related to it, we can understand few more things about it by going through each of these points. So first, uh, so if you uh, operate this displacement operator on your ground state of your harmonic oscillator, then uh, what you get, or what is your, I mean, the outcome that will be defined as your coordinate state. So that is our first task to do. So first we have to operate our displacement operator on the ground state. So using which we construct, using this displacement operator, we finally construct our coordinate state alpha. So right. So yeah. So again, let me write d of alpha as your displacement operator. And also remember we had another relation, d of alpha equals to alpha star alpha star a. So yeah, so this is another way to write. Again, you can to get from this expression of d alpha to d alpha, you can use the ECS rule as we uh, I mean discussed right at the beginning, right here. So yeah, uh, so you can use uh, yeah, you can use this BCS rule to write this your I mean uh, d alpha to, you can re-express your displacement operator in the following way, which I just wrote here. So this, so right, then you have to operate this d alpha on your ground state. Then you can write alpha as d alpha 0. Then your d alpha is exponential alpha a dagger minus alpha star a, then acting on 0. So uh, so what I can do here, so first uh, there is a I mean, okay, so to, so you see, if you would use this expression, I mean, if you use d alpha which we have written here, and use this expression to operate on ground state, like then you write exponential of this thing with acting on your ground state 0. then how will you proceed with from here? So to proceed from here, you will have to, the only way to go from here is to expand this exponential operator. So you know, you can you for any exponential of x, whether it is number or even if it is operator, you can write this as 1 plus x plus x square over 2 factorial, and so on, it goes like. So if you do that thing right here, so it will be identity plus, for operator it would be identity. So if x is your operator, then this is your identity operator, then x operator, then x square operator. So yeah, so identity plus alpha a table minus alpha star a. uh, and yeah, one of the properties that we saw in the previous case where we derived these two things. One property which we found is unitary, d alpha dagger, d alpha is identity operator. So, and second, we also saw this d alpha dagger a, d alpha is a plus alpha, and also d alpha dagger d alpha is a dagger plus alpha star. So that is basically another property of displacement operator, that is or from which we know or which we know by its name, why it is called displacement operator. You see, this it is if you uh, operate this I mean, what do you say, I mean, uh, if you like uh, if you use this a operator or using this d alpha, you can displace uh, a operator by some alpha, or in the other case you can displace a dagger by some alpha star. So by that, its name has come. I mean, the name that we are calling displacement operator, because it displaces a operator by alpha. That is in phase space. You can understand like it displaces a and a dagger. Uh, so yeah, that was some bit of information, but yeah, like those are some important features. First, unitary and displacement feature. So yeah, so we were right here. I was telling like if you use this exponential expansion of this exponential operator, so you will get something this way: alpha a, so 1 by 2 factorial alpha a dagger minus alpha star a, that is square. So that means you have to you have two I mean two such operator, like I mean, if you call this as a, so a square is like a uh, and if you are operating on 0, you first have to operate a on 0, then again whatever you will have, you will have to operate this again on this. I mean, if you get something, let's say you got something a of 0, then you will act a on here. So you see, I mean, there are, so you see it's always a difficult thing. I mean, if there are more such terms. I mean, here you have square, then the next term would be cube, then the fourth order term in power, then fifth order in power term, and likewise it has such, I mean, many terms. And you see that like if you calculate this way, it is quite difficult. I mean, in the sense, you have to first, for this case particularly, for a square, you have to first calculate. I mean, a, and then this again you have to operate on a in this way. So if you would use this relation, it would be bit easier. So that how you can see right here. So suppose if you start constructing alpha using the other form of displacement operator, that is uh, e of minus half mod alpha square, then e of alpha A dagger, then E of alpha star A acting on 0. So you see this if when you see here, and this E alpha star A acts on 0. So what it will give you, uh, so again if you would see 1 plus x squared, if you use this form for this case, uh, minus half alpha square alpha a dagger 1 plus alpha star a plus whatever you have, uh, alpha star a by 2 factorial, so this is square, you have this thing. So you see carefully, uh, here in this factor which is in bracket, every every term here, if you operate this on 0, it will give you 0. Why? Because you have a operator when acts on 0, it is always 0. So you see, a operator is always there. It's from second term of this bracket, from second term onwards, you will always find. Here you have a, then you have a square, then you have a cube, and so on. So you will always get 0. Only first term, that is identity operator, if acts on 0, it will give you 0 again. So that is uh, minus half of alpha square, alpha a dagger, and 0. Because only identity operator, uh, like this or this state 0 is survived only of this identity, only because of this identity operator. Yeah, and same way you can see, if you do the same similar thing for minus of alpha square, again you expand this, 1 plus alpha, uh, yeah, 1 plus alpha a dagger plus alpha a dagger square over 2 factorial plus other terms and 0. Uh, Here you will find, first you will have 0, and second, from second term, you can use this a dagger when acting on any nth state. It is basically n plus n plus 1, n plus 1. So using this rule of this creation operator, you have alpha root 1 get 1. Then in the second term you have alpha squared by 2 factorial, and here a dagger will act twice, so a dagger 0. So so on, you have other terms, so you have this of alpha square get 0, then alpha get 1. And from here you see, if when a dagger acts on 0, it gives you root 1 1. And then when a dagger again acts on 1, it will give you uh, uh, yeah, it will give you root 1 times root 2 and 2. So so overall, you will have, in this, from this term you will have alpha squared by, uh, let me write, you can write the second term in the following way. If you rearrange and simplify the factors properly, you can write this alpha squared by 2 factorial, square root 2 factorial times 2. And the same way you will find, you can write the third term, which I have not shown you. The third term will be, uh, I mean, the third term will be alpha a dagger cube by 3 factorial. So you will find the third term would be something this way. So and this way it continues. So using that, I mean, the or for the nth term, you can write it as alpha n by root n factorial, and yeah, and so on. It will have more other terms also because this is an infinite series. So, and from here you can write alpha, which we started. So the first factor, prefactor, which we have right here, minus of alpha, half of magnitude alpha squared. Then summation n goes to 0 to infinity, uh, alpha to the power n, square root of n factorial over n. So yeah, this way you can construct your alpha using your displacement operator. And remember, we used this form of displacement operator to get our answer. If you would have started with this, you will find many problems. I mean, it is quite difficult to compute. Here, you see, you have two such terms in this bracket. And if you take square, it will give you a dagger a square operator and a dagger square operator, and you would have difficult to achieve this kind of form which we just found. Here it was luckily you see one of the exponential just gave almost no. Uh, I mean that was this part at least when you operate this operator on this state, you found just zero because e of alpha star a gave you only zero that we saw just right here. So yeah, this thing you can write as this thing under the bracket, and when this whole thing ends on zero, it gave you only zero. And then only work you have to do with only this exponential, which is you see only one term is there in its power, in its exponents, in its exponent. So yeah, so yeah, this was some task you need to do to get this proof. So uh, did you get this part or any questions? Like any questions you can speak. Yeah, so okay, so if there is no question, we can move with for the second what we have. So first we saw how we can construct this alpha, your coherent states. So here you see the coherent state that we found here is an infinite. Uh, it contains indefinite number of quanta, which we begin at the at the start of this session. So we said like this coherent states are made of many number of infinite number of eigenstates, linear combination of eigenstates, and this alpha has other properties that which we discussed very briefly because this is very important in understanding various Hamiltonian, various quantum systems related with photonics or basically quantum optics, where this alpha is basically treated as some kind of I mean, it basically gives some sort of classical nature of state uh, uh, based on the given quantum system, and and using that you can explain things like, I mean, you can explain this state can explain or basically gives you a state of classical light in quantum optics context. So yeah, so this is important in that regard, and also has many other significance. So right, then we have then compute the inner product of two distinct coherent states. So what will be the inner product next? So we can see. So the or yeah, let's consider two distinct. Let's consider two distinct coherent states. That is uh, alpha and beta. So then we have to basically evaluate uh, alpha and beta inner product. So this is what we have to calculate. So yeah, first you see beta, we know like as we found here. So this is you you can write same way beta as your another coordinate state with minus half of beta square, then summation and 0 to infinity beta to the power n and factorial n. So and yeah, you have beta is your distinct coordinate state, and same way you have alpha. And to compute inner product, you have to take this. You see this bra of alpha is multiplied or is uh, operated with ket of beta. So that means you have to calculate complex conjugate of alpha, or basically you have to take dagger of alpha. So first task is to take this dagger of alpha. So that will give you so alpha something alpha goes as exponential of magnitude of alpha square, and then summation n going from 0 to infinity alpha to the power n and factorial. And so yeah, so this is your alpha, get alpha. You have to take dagger of it, then that will give you uh, alpha equals to. So the first term is just a factor, it's just a number because magnitude of alpha square, and you are taking exponential of that, exponential of magnitude of alpha square. So it's a number, it's a real. When you take alpha is a complex number, but if you are taking magnitude of alpha square, so it's basically a real quantity you have. So its dagger is basically itself the same thing, and then you have summation and goes to 0 to infinity alpha to the power n dagger. Then here you can write alpha to the power n dagger. So alpha is a complex number. So as I said, if you take dagger of that complex number, it's basically conjugate of that number. So alpha conjugate is star to the power n. Then in the denominator you have just square root of n factorial, which will remain as it is. Then ket of n will become this bra of n. Right. So you have got this complex conjugate form of alpha. So then you can take the inner product. So here you can take alpha and beta inner product. So from both from both the alpha and beta, you have this prefactor. Uh, so I can pull that at the front, and that will give you exponential of minus half alpha square plus beta square. Then summation, uh, let me use different index here. So uh, let me call this index as m. So I'm denoting, because these are distinct states. It is, I mean, it is best to use different notation. So yeah, yeah, it's always whenever I'm working with two distinct states, or some vectors or anything. It is, I mean, best practice to have two different index. Yeah. So I have made all the n's to m for the beta coherent state. Yeah. Then over here we have n as usual. Then I have to also, yeah, fine. Okay, it's fine. So now we have m going to 0 to infinity and also n going to 0 to infinity. Then uh, then we have alpha star to the power n, beta to the power m, then n factorial, and yeah, same square root again at m factorial, and n m inner product. So yeah, so this is what you will get if you try to do this inner product. And you see here, this thing is again your familiar inner product term, inner product factor, where you and so these are two different eigenstates of your quantum harmonic oscillator. So uh, so if these are two different quantum states of quantum harmonic oscillator, these are eigenstates. So they are basically orthogonal. So we denote those orthogonal states by Kronecker delta. So they are normalized. From this Kronecker delta, it means they would be either one or zero. Uh, yeah, and from here you can write exponential of minus half uh, alpha square plus beta square infinity alpha star and beta star m n factorial delta nm. So yeah, so here if n is not equal to m, then the whole thing is zero. So n has to be equal to one. So n has to be equal to m. If you want to say any non-zero non-zero contribution from this inner product. So yeah, only non-zero contribution will come from uh, n when n is equal to m. But otherwise, if n is not equal to m, then the whole thing is zero. So uh, right. I mean, uh, so whenever this m runs from 0 to infinity, n also runs from 0 to infinity. So whenever m is equals to some number, let's say m equals to 1, then n is also have to be 1, uh, such that you will have some non-zero term. If you have m equals to 1, n equals to 0, you will get 0 from that particular uh, summation term. So the only summation, so I can write this as minus half of, summation n equals to 0 to infinity alpha star beta to the power n over uh, yeah, alpha star beta to the power n. Then n and m are equal. That means n factorial. So yeah, so so for non-zero term, you should have n equals to m. So if n equals to m, then that means uh, your m is n, then n factorial times n factorial is n factorial square, and you have square root that is n factorial. So in the denominator you form. And same way, on the numerator you see this power will become same in both the alpha star and beta star. Alpha star and oh yeah, this will be not beta star, alpha star and beta. And yeah, so now you have you see this thing which is written here is basically something written in the form x to the power n factorial summation n equal to 0 to infinity. So this is like e to the power x term. So yeah, I can write that as half alpha. Yeah, so I can write this as e to the power beta star uh, alpha alpha star beta. So yeah, so I had so finally I have uh, yeah, finally I have this. So uh, so from here you can see the inner product of alpha and beta is giving you something this. Then if you take inner product of, let's say, beta and alpha, you will find exponential of minus half alpha square plus beta square. So you can do the same exercise back again, but by reversing this beta and alpha, you will have exponential beta star alpha. Uh, this beta and alpha will reverse here. So uh, so here I'm just trying to. So I mean, we found the inner product, like uh, the inner product that we wanted to calculate. Uh, so yeah, so this inner product we found it. That is this thing right here. So if you would have wanted to calculate this inner product in this way, then this would have been this. But using this, what you can show, um, uh, alpha beta inner product, if you multiply with the inner product of beta alpha, so that is like taking inner product magnitude square, magnitude or mod square of this inner product will give you basically uh, exponential of minus. So you just have to multiply these two things. The right hand side which you have this one with this, if you multiply, you will get a minus of alpha square plus beta square minus alpha star beta minus beta star alpha, right? And this is nothing but exponential of minus alpha minus beta uh, mod square. So, so the uh, so finally what we have, alpha and beta. If you take inner product square, you will get exponential of minus alpha minus beta mod square. If get alpha equal to get beta, that means the same state. If you take the inner product of same state, basically uh, when we do the magnitude square of the inner product of your same state, it means you are uh, taking the normalization. So that should be one. So if you do that, so if a alpha equal to beta, then you find mod square equal to alpha. That means uh, uh, alpha is a normalized state. So okay, so yeah, we wanted to show the inner product, but using this inner product, we also proved like this alpha, this coherent state that we have been defining from the beginning, is also a normalized state. So yeah, so if any question you can ask anything. I know this is quite very long exercise, but if you missed anything at any part, or something else also, if you other than this also, if any other topic related to any basics or anything you couldn't follow or you have any doubt, you can ask. Uh, any questions? Any questions or you follow? Yeah. Do you have any questions or? Okay, if there's no, we can move ahead with the uh, next person. So next we have to compute this mean number of quanta. So what do you have to do? So you have to calculate average value of number of quanta uh, contains in the core state. So for average, that like how we have been doing in quantum mechanics, using the same approach, uh, we'll see how we can compute the average of uh, number of quanta. So by number of quanta, we mean a number of the n basically. Uh, so mean number of quanta, mean number of quanta. It's basically, it means uh, average. Uh, uh, you have to calculate average number of quanta in core state. So you have to calculate the expectation value of n operator n coherent state. So n will give you the mean number of uh, what will give you the number of uh, average number of quanta or average number of uh, eigenstates of harmonic oscillator uh, associated with your coherent state. So average number of quanta, how many quanta is contained in your uh, coherent state alpha. So it's average number to basically that what it means physical. So in for harmonic oscillator, you know this n operator is given as a dagger a. So uh, so then uh, if you calculate alpha and then n dagger of alpha, you will get alpha a dagger a alpha. And so from the definition of coherent state, which we started our discussion, we know coherent state are the eigenstates of lowering operator a of alpha is basically equal to alpha of alpha. So this is keeping this in mind. So even you can check this from the alpha that we constructed using displacement operator. So so over here you can also check a of alpha will give you this alpha of alpha. So yeah, so you can check this and you can uh, verify yourself where you'll find this is how coherent state has been formulated. So yeah, so using that and also if I take conjugate of this thing, so I will get uh, uh, what I mean, I can write this part as a of alpha conjugate and a of alpha. So a of alpha is alpha alpha, and so here I have alpha alpha dagger alpha alpha. So using this I have uh, alpha alpha star alpha and alpha. So this basically gives me mod of alpha square and alpha alpha, and we know alpha alpha is 1 as just we saw it just before, just moments back right here. That is, these are uh, normalized states. So alpha alpha is 1, so this is mod alpha square. Okay, so and so this is your mean number of quanta associated with your uh, in your associated with your coherent state. So, or you could have also done this using this way, where uh, you could have started alpha uh, a a dagger a and alpha, and you could have uh, used the idea of I mean I wanted to say. Uh, There is, the one which we did is a easier way, is an easier approach to come to this conclusion, alpha square. Or suppose in a case where you don't know, or you are not sure about uh, a of alpha is not alpha alpha. I mean, we know this because that is how we have defined, but you could have checked this through without using this property by uh, using the coherent state that we found right here. So using this coherent state, so you can use directly this relation here. So if you could have used this n, I mean this alpha, the definition that we know. So it will have minus alpha square summation n alpha star to the n alpha n by n factorial then m and yeah. So using that this approach also you could have done, you would have find this to be alpha square. But the one which we saw right here using this definition of coherent set, we can easily get or prove this to be alpha square. So yeah, uh, okay. Then I think next we have uh, some more questions right here. So we have next task is to calculate uh, the expectation of x and x squared, b and b squared in this coordinate alpha, where x is defined to be this the as usual uh, momentum or position operator defined in the harmonic oscillator system. So these are not difficult to see. I mean, these are you are already familiar with how to computing. Uh, you are already familiar with the computations of expectation of position momentum operator for a quantum harmonic oscillator. Uh, but this time you are doing this computations of this expectation value in coherent state. So that is the only the difference that you see. So yeah, we can see quickly some of this. Suppose um, first maybe we can see the expectation of position operator. So just like how we saw the expectation of uh, uh, number operator, then the same you see expectation of position operator in coherent state. So alpha and position operator is defined as s bar h bar 2m omega, which is under square root uh, a plus a dagger alpha. This is equals to h bar over 2 omega uh, alpha a plus a dagger alpha and yeah. So h bar 2m omega alpha a alpha plus alpha a dagger alpha. This will give you h bar 2m omega. And A of alpha is alpha alpha. So uh, and alpha is a normalized state. So you will have alpha, and from the second one you will have alpha star, because you can see. I mean, is alpha alpha star. So using this, you can write this as alpha star. So yeah, so this is your expectation value for position, and same way uh, for x square you can calculate. So why I'm doing this, like I mean, at the end there is another important meaning that we will see. Using this expectation values we can define an uncertainty, because uncertainty you have to calculate this expectation values of x and x square mean values, and then we calculate the standard deviation. So if I quickly calculate the expectation of x square right here, so this will be x square will be, you just operate uh, x operator twice. So I have h bar over 2m omega. So here you will have a square plus uh, a dagger plus a dagger a plus a dagger square alpha. Then this will give you h bar over 2m omega alpha a square alpha plus alpha a dagger alpha plus alpha a dagger a alpha plus alpha a square or a dagger square alpha. So yeah, so from here you will see this will give you alpha square, and this will give you alpha star, and this will give you alpha star. Yeah, this will also give you alpha star, and this will give you alpha star square. So you have x square average as h bar by 2m omega uh, uh, alpha square plus 2 alpha star plus alpha star square. Yeah, that is what you will get here. So, and for uh, momentum operator, you will find for as the same way you will calculate the average for momentum operator. Um, like this will mh per omega by 2. So these are similar computation. I'm not showing in detail. So alpha heidegger alpha minus alpha a alpha, and this will be minus I h bar m omega over 2, then alpha minus alpha star. Yeah, so same way p square also you can calculate. So uh, like I'm directly writing down the value here, 1 minus alpha minus alpha star square here. So yeah, okay, so from here what you can see, if you calculate the uncertainty like the standard deviation sigma x square, which is uh, x square average minus uh, uh, x average square, that will give you h bar 2m omega. You can check that, and sigma p square will give you p square minus p average. That will give you h bar m omega over 2, and this if you calculate sigma x sigma p, the uncertainty principle that we know. So accordingly, you will get from this computations that we had over here. So it gives you h bar m omega by 2. So this gives you h bar by 2. And from uncertainty principle, we know Heisenberg uncertainty principle says the minimum uncertainty associated with your measurement of your, I mean, for a given system has to be h bar over 2. And you see, when we computed using uh, when we computed the averages using alpha as our coherent state, I mean, we computed all these averages in our coherent state alpha, we are getting this minimum uncertainty. So this is why at the starting I also tried to motivate these coherent states are basically corresponds to minimum uncertainty state, in classical states we have how the definite states, I mean, they do not have any uncertainty. So that is why this coherent states are usually treated in a classical state correspondence for various contexts. So so yeah, alpha we can write as alpha corresponds to minimum uh, uncertainty state, or basically we can say, or they correspond to classically behaving states. uh, right. Okay, so any doubts or questions here we can. So any questions or anything which you will not follow. By the way, are you going through the lectures, right? Hello, Hanuman Prasad, uh, or anyone. Uh,
So, the external exam is in multiple choice or
uh,
object descriptive type?
the final exam you're talking about.
Yes, yes.
Like is I know, like, I mean, it would be a mix of both. I mean, there would be I mean, MCQ would be there, and also some subjective type also. So I mean, it could be more clear if you directly talk to the NPTEL, so they would let you know. But as far as I know, I think it's mix of both. And yeah, I mean, if you follow the assignments and the lectures well, and yeah, if you follow all the related questions that are discussed in all the places that you've been in this registered course, then yeah, it's not a difficult task to appear for exams. Or I mean, yeah, exam would be fine, like, there's no need to worry about. So it's just you have to follow the materials well, your course material properly. Then yeah, that is enough.
Mhm.
Anything else you wanted to?
This subject is very tough to me because my background is electronics and communication.
Oh, okay, I see.
So the little bit is odd. Here the total that means physics completely related to the physics, no?
Okay, okay, yeah, yeah,
So that,
yeah. So I mean, you know, knew something about. I mean, you know, basic quantum mechanics.
yes, yes.
Okay, so if you follow basic quantum mechanics, then probably you can follow this course well also. But yeah, you just have to. I mean, you need to have some good grip on your basics of this quantum mechanics, and then you can proceed. Like I mean, gradually you will found things like properly understanding. It's not like something you can have it in a go. So yeah, it will take time, but yeah, just keep going through the lectures and basics. If you do not understand the basic, I would suggest like just follow uh, David Griffith books. That is quite a simpler book to understand. And yeah, other than like you can like I mean follow the NPTEL course that you are doing, and yeah, you can ask doubt whichever at whatever point you do not understand or any question related to quantum mechanics if you are having difficulty in dealing with the things then.
Because simultaneously, I can already register in introduction to quantum computing.
So
So
that
both
that you have finished
program,
or that you are doing now?
not finished yet. But that is a 4 week program.
Okay, okay,
So
I see.
that is
Okay, okay. Yeah,
simultaneous.
I mean the basics. You need to spend some time on basics, and if that is once you have some good amount of basics on that, then you can get here. Because like you need to have that proper mathematical picture how we work
Oh,
on quantum mechanics. Like those mathematical picture is quite different than how you are generally familiar with other mathematics. So this is again very different from Newton and mechanics you would have seen, like the mathematics, the how we define states here, and there are no such notion of states in classical theory, or rather they are very fixed states. Here we have a probability notion, so there we have a definite picture, a notion of definite picture. So yeah, there are a lot of contrast. It's quite a big shift if you are going from classical mechanics to quantum mechanics. You need certain things to absorb first from your basic quantum mechanics course level. Then you can follow this course well. Yeah, yeah. Take some time. It will you can follow.
okay.
Yeah,
Thank you.
yeah. Thanks. Yeah. Anyone else? Any other problem? Again.
And one more is answer.
Sorry, sorry. Uh, I couldn't hear you properly.
Different questions answer.
Yeah,
So uh, that means we are sending you. That means handwriting, or you can by soft copy submitting
yeah,
either handwriting or submit soft copy.
yeah. You can write down your answers like anywhere. If you, I mean, like handwritten notes only. I mean, handwritten. You can write down them and then you can scan it and submit in your portal. Like there would be a submission uh, place within your portal. You can just scan it to your written answers and then
Okay.
just post it on your portal.
Okay.
Mm, yeah.
So, sorry, you're, today also I'm joining late at 5 o'clock or 5:15.
Okay, okay.
But and
So
so in your classes you are mentioning that means you are telling assignment questions also
yeah,
answering.
yeah. I am doing some related assignment questions also. Like I may not be exactly same, but something similar to the same, or sometimes it is also same. So if you need particular help in particular assignment problems, you can say we can discuss that as well. So There is no problem with that. And yeah, and other than assignment, like the topics that I discuss or courses I discuss, it has to be something related with that particular week's topics, which has been described, which has been taught by the instructor, or some questions related to the assignments, or yeah, or sometimes exactly the same questions also we discuss here. So that was usually our plan, but there is no such strict thing to go with. If you are having some problem in understanding something else, we can also discuss that. There is no problem with that.
Okay, thank you.
Yeah, yeah. Any more thing like anyone wants to say or ask if they have anything to share? Uh,
Excuse me, sir.
yeah, yeah.
Sir, as I have registered only 2 days before,
Okay, okay.
so I didn't attend previous problem solving sessions. So is
Okay.
there any recorded classes available or?
Yeah, yeah, I think it is also shared with you. If you go, I mean, in your this NPTEL portal, your account, I mean, open your account with, I mean, your NPTEL portal account. Then
Okay,
you find somewhere, I think I forgot the place where you search around within your NPTEL portal, you will get it. There is a place where
okay,
all the recorded session and this presentation material are kept there. You can
okay, sir.
go through that link and you will access. You can able to access them.
Okay, sir. Okay, sir. Thank you, sir.
Yeah, yeah. Yeah. So anything more? So we are almost I mean, we are almost to six. I mean, we are the time is up right now, so we can uh, discuss any other questions maybe next week. But if there's any particular questions from your side or any problem or doubts or any comments, you can share here. Uh, any questions or okay? So if there's no question, maybe we can stop here. We can meet next week again with some more questions and more doubts if you have. And yeah, yeah. So yeah, we can talk again uh, next week. So yeah. Thanks and bye.
Thank you, sir.
Yeah.